All right, here it is. This is what we've been working our way up to in this unit. We've learned about stars. We've learned about how they form. We've learned about how we gain information about them through our understanding of electromagnetic waves, all so that we could get to this question. How did the universe get to be the way it is today? And today, we're going to start to address that question. We've got 3 learning targets for this part of this unit, and today's lesson is going to focus on the first one, stating the events that happened as the universe formed, as set out by the Big Bang Theory. And no, I don't mean the TV show. Oh, and by the way, when we say theory in science, we don't mean the same thing as people who use that word in casual conversation. When you or I, talking as average human people, say that we have a theory about something, we usually use that word to mean that we have a guess. And it might be an evidence based guess, but it's still a guess. It's not something that we have proof for. On the other hand, a scientific theory is something a little more robust than that. In science, when we say theory, we mean something that is evidence based. We mean that it's something that we've tested and that has held up as the best, simplest possible explanation for the data that we've got. And if the data changes and we get reliable data that doesn't fit the theory, then that theory is subject to change. But for the moment, it is our best understanding of the way that something works that's supported by evidence and based off of data. All right, so let's get started. And we've got to start with what came before the universe, which, well, we've got ideas, but we don't really know. Here's what we do know. In the instant before the universe as we know it came into being, all of the matter in the universe was squeezed down into a point the size of a single atom. How did it get to be that way? Well, that's still the subject of consideration. But there are 2 things that we know for sure. Number 1, we know for sure that all of the matter of the universe was there in that point. How? A little thing that we call the law of conservation of matter. And what that tells us is that you can't make matter out of nothing, and you can't destroy it either. All you can do is change it from one form to another. So we know that all of the matter that's present in the modern universe had to have been there in one form or another at the start of the universe. And number 2, we know that this state, this compression of all of the matter in the universe into that tiny point, was incredibly unstable. Many of you all chose to learn about radiation, and all of you learned about what an unstable nucleus looks like when we did that Build an Atom PhET lab. Imagine that, but on a cosmic scale. There's no way that that state can be stable, and turns out it wasn't. So time begins about 3.7 billion years ago. And that instability that we just mentioned results in a rapid expansion of everything. The universe begins to inflate, rather like a balloon. And here we see a nifty idea that we briefly mentioned when we talked about Albert Einstein and his theory of relativity. Remember that equation, E equals mc squared, which, remember, he came up with as an afterthought to his real work, which is bonkers because it's such a revolutionary idea. Because what that says is, yeah, we have this conservation of matter thing. That's great. Can't create it out of nothing, can't destroy it. But what you can do is convert it into energy. That's what that equation there is saying. You take mass, m, You multiply it by a constant c, which is the speed of light, and you do that twice, and you get how much energy that matter can be turned into, or capital E. Just ridiculously radical idea. So what's happening is that this expansion is not only pushing matter out into the universe, but converting tons of that matter into energy. Remember that, because that will be important next week when we get into evidence. Our baby universe is now just about a second old. We've moved forward in time, and a lot of stuff has happened to it in that first second. We've got tons of energy, and we've got matter, and we've expanded it all from the size of a single atom to the size of a softball and beyond. But that matter isn't yet in a form that looks like the matter that's around today. It's quarks and electrons all mashing around together in a high energy plasma soup. And it can't stay like that forever. It's just not sustainable because the universe is cooling down rapidly. In that first second, the universe has gone from a temperature of 1 octillion degrees Celsius to a measly 100 billion degrees Celsius, which is still ridiculously hot, but significantly less ridiculously hot than it used to be. And because it's significantly less ridiculously hot, the matter in the early universe has less energy at the 1 second mark than it had right at the beginning, which means that as things collide with each other in that plasma soup, they're going to start sticking together because they don't have the energy to break apart anymore. So in that first second, we begin to see the formation of some familiar stuff, protons and neutrons. Let's fast forward ahead a little bit and check in on our newborn universe around the 3 minutes post-expansion mark. At this point, a lot of the matter present has continued to condense into our familiar subatomic particles, and the universe has continued to cool off. We're now at about 100 million degrees Celsius, down from the 100 billion that we had after that first second. But at this point, there's something that has remained constant throughout the birth of the universe. It's dark. This cloud of subatomic particles, this seething plasma soup, is still so tightly condensed that nothing can get through it. But that's about to change. Well, I say about to change, but that's a relative term. We have to get to about 300,000 years old, which, relatively speaking, is still very young, but we fast forwarded quite a bit. And during that time, the universe has continued to cool off. When we hit the 300,000 year mark, it has dropped to about 10,000 degrees Celsius, which means that it's cool enough to start forming atoms, specifically hydrogen and isotopes of hydrogen, which made up about 75% of the early universe at this point, and helium, which made up the other 25%. And when those atoms start forming, there's now enough space in the early universe for light and other electromagnetic waves to start shining through. By the way, as a point of interest, the universe today is still very close to that 75% hydrogen, 25% helium ratio. Obviously, we've got a couple more things. The numbers aren't quite exact, but still very, very close to that. We're jumping forward again. This time because we're going to start to get predictable. Now that we're forming atoms, what we've got is great big clouds of hot atomic soup. And we know what those are. Those are nebulae. It's just a cloud of gases and energy. And every nebula is going to do exactly what we already know that nebulae do. Gravity is going to do its thing, atoms are going to start to stick together, and they're going to keep on sticking together, forming larger and larger clumps until there's enough mass to create stars, which, when we hit around the 200 million year mark, is exactly what's going to start happening. And from that point forward, we're pretty much going to see exactly the kind of universe that we've got now, which means that there's really only one more significant time point that we've got to hit. And that time point, of course, is when the universe is just over 9 billion years old, which was about 4.6 billion years ago from right now, the moment when our solar system formed. And that's the moment where we're going to pause the clock, because what happens next, well, that's the subject of our next unit, and we don't want to get too far ahead of ourselves. Now, let's clear up a couple of things before we get too far ahead of ourselves. First of all, you heard me right in the beginning. I said expansion, not explosion. And this is a pretty common misconception, that the Big Bang was an explosion. And it's easy to understand why people would think that. There was a lot of energy, a lot of heat, but think expansion, not explosion. Imagine a balloon being blown up, not a bomb going off. Because really, the early universe would have been more like something inflating than something exploding. And we kind of have this popular image of the singularity, meaning all of the matter condensed down to that single point, being kind of like a fireball in space, or of that early expansion looking like that. Not really, because outside of that single point, there was no space. Around that singularity, there wasn't anything, because all of the matter, all of the stuff was in that point. So, imagining something like a fireball up in the sky isn't really all that accurate. So, what comes next? Well, next week, we're going to get into that whole evidence piece. And I'm going to take you through several pieces of evidence that we have that indicate to us that this is the most likely scenario. This is probably how the early universe got to be the universe that we know and love today. So, for now, we're going to start working on a little project. All right. So, when I was an earth science student, we had to do this project, and we got big sheets of basically receipt paper, and we had to make a timeline to scale of the formation of the universe from Big Bang to the Earth, and the Earth in its modern form. And let me tell you, that project was ridiculous and just incredibly finicky. And you had to squeeze so much stuff into the end part of that project. I'm not going to ask you to do that. What I am going to ask you to do is make yourself a timeline. Specifically, a timeline of how the universe got to be the way it is now. And I'm going to show you what I'm looking for here. You're welcome to do this on paper. I do recommend that you do it on Google Drawings instead. So here I have a beautiful drawing. It's just gorgeous. And the first thing that I'm going to do is go into my page setup and I'm going to make it a custom width because I want it to be a lot wider than it is right now. About 20 by 7.5 should be fine. Nice, fills my screen. And I'm going to insert some shapes. You can pick whatever you want for your bubbles. How about some explosions just for kicks? And I'm going to make 6 of them. And I'm noticing already that the size that I've made these, I'm going to need more space. So I'm going to make them a little smaller, but you could absolutely decide to just make your screen wider. That would work too. So once I've got 6 of these beauties in here, I'm going to label them. And I'm going to have the same time points that I gave you in the video. And I'm going to fill in somewhere underneath these time points the important events that go with them in the formation of the universe. However much detail you feel like you need, but you've got to get the main ideas across. And this isn't going to be the end of this project because we're going to add to this next week. We're going to add in our pieces of evidence and what part of this timeline they attach to. So you're going to make this and you're going to turn it in this week, but make sure that however you set it up, you leave room to explain evidence and to explain what that evidence is and explain what it means, which is why I really encourage you to do this one digitally. I'm not going to stop you from doing it by hand, but make sure you have a plan for adding extra space to it if you need to. All right, this is the point where I am going to sign off. You've got work to do for this week. I've taken you through your demonstrate knowledge task for this week, so you should be in good shape to do this. But remember, you've also got to do another gain knowledge, which if you took notes, that you're in good shape. But if you didn't, make sure that you pick another demonstrate knowledge or go back and take some notes. And make sure that you do one of your experience science and nature tasks for this week. As always, be good, be safe, be kind. Don't do anything I wouldn't do. Wash your hands and look for evidence of the Big Bang Theory to come next week.